We are back, and I'm going to try and finish this out with one video. We'll see how time goes. Maybe we can do it. So we're looking at example 2, and we're given f of x is equal to negative 2x, negative 2 cosine of x minus x, and we're going to use the second derivative test to find whether f has a local maximum or a local minimum at x is equal to pi over 6. We're going to justify our answer. So first thing we need to do is we need to find the first derivative, and we need to see if this is equal to 0 at this point. So that's what we're going to do. The first derivative, f prime of x, would be the derivative of negative 2 cosine of x would be 2 sine of x, and the derivative of x would be minus 1. And so now we found the derivative. We need to evaluate it at this point. We need to see if this thing is 0. So f prime of pi over 6 is equal to 2 sine of pi over 6 minus 1. So f prime of pi over 6 is equal to 2. And sine of pi over 6 is 1/2. So 2 times 1/2 minus 1. So 2 times 1/2 is 1. 1 minus 1 is 0. So at pi over 6, we have a horizontal tangent line. If we have a horizontal tangent line, that means we can have a relative max or min. So now we need to take the second derivative. So we'll take our second derivative, and f double prime of x is equal to, the derivative of 2 sine of x would be 2 cosine of x, and the derivative of negative 1 is 0, so that just goes away. And we're evaluating our derivative at 2 cosine. We're evaluating it at pi over 6. Whoops, I should have been pi over 6, excuse me. So 2 cosine pi over 6. So f double prime of pi over 6 is equal to 2 times. Cosine of pi over 6 is the square root of 3 divided by 2. And so this simplifies to the square root of 3. So my second derivative at this point is positive. And we have a horizontal tangent line from our first derivative at that point, right? So what this means, it's positive, that means that we are concave up. So it looks something like that. If we're concave up, that means we have a local min. So let's say by the second derivative, here's our justification. By the second derivative test, x equals pi over 6 must be a local min. So my first derivative was equal to 0 at pi over 6. So if my derivative is equal to 0, we have a horizontal tangent line, or we should have a horizontal tangent line. My second derivative was positive. That means we're concave up on that interval, and we can just keep going from there. So we've jumped down to example 3, and we're going to use the second derivative test, if possible, to find the relative extrema of this function. We're going to justify our answers. So the first thing we need is, if we're looking for extremas, we need to take a derivative. So f prime of x is equal to 6x squared plus 6x minus 12. If we're looking for extrema, we need critical values or critical numbers for our derivative. So we're going to take this derivative, we're going to set it equal to 0, and we're going to solve and figure out where those horizontal tangent lines occur. The first thing I'm going to do, just to make it a little easier on myself, is I'm going to factor a 6 out, and then we have x squared plus x minus 2. We're setting all of that equal to 0. I can divide both sides by 6, and my 6 goes away, and we're left with x squared plus x minus 2 is equal to 0. That factors as x plus 2 times x, whoops, not x plus 1, x minus 1 is equal to 0. We're going to set each one of these factors equal to 0 and solve. So we end up with x is equal to negative 2 and x is equal to positive 1. These are my critical numbers. These are where my horizontal tangent lines occur. Critical numbers, horizontal tangent lines. And those things all occur there. So that's fine. These are the numbers we really need. So now we do have some zeros, right? We have some horizontal tangent lines. So we need to find our second derivative. And then we're going to evaluate it at these points because we need to see at these x coordinates, is my second derivative, does it have a positive or a negative value? So that's what we're going to do. Let's take the derivative of our first derivative. So f double prime of x is equal to, looks like we're going to end up with 12x plus 6. So there's our first derivative. We have to evaluate it at both of these coordinate points. So f double prime of, let's start with negative 2, is equal to 12 times negative 2 plus 6. So we're substituting that in. 12 times negative 2 is negative 24. So negative 24 plus 6 is negative 18. That's a negative value, and that means because my derivative is my second derivative is negative, we're going to have a relative max at that point. We need to evaluate this thing at 1 as well. We need to take our second derivative. We need to evaluate it at 1, and so we get 12 times 1 plus 6. So 12 times 1 is 12 plus 6 is 18. That's positive value for our second derivative, which means we are concave up. So we could also build a table of values for this thing to try and figure out what's going on. And I did that in the notes. And so instead of me building the table of values like I did in the notes, I'm going to let you look at that just to save time. So we have a relative max at x equals negative 2 and a relative min at x equals 1. And you can build our sign chart, right? We can build our sign chart like we've done before with using our critical values, negative 1 or negative 2 and 0. And we know we've got f prime and f, and you guys can build that from the notes just to save some time. Let's go on to example 4. So now we're given the derivative f prime of x is equal to g of x times the quantity x squared minus x minus 6. And they give us some values. They say g of 3 is negative 2 and g prime of 3 is 7. And we're going to determine whether f has a relative max, relative minimum, or neither at x equals 3. So the first thing we're going to do is we just need to evaluate this guy. We're going to take our f prime of 3. Right? So we're going to take our derivative, f prime of 3. We're going to evaluate this thing at 3 because we need to see if it's equal to 0 if we have a horizontal tangent line there. So we start off with our g of 3. And then we're just substituting this in. We're evaluating. We get 3 squared minus 3 minus 6. And so for some of these things, we need to think a little bit ahead. This is 0, so it doesn't matter what g prime of 3 is, or g of 3 is, excuse me, because this is 0, it doesn't matter, this is 0. So at 3, when x is 3, we do have that horizontal tangent, so we do have the possibility of having a maximum or a minimum value. So that means we need to do everybody's favorite. We need to take the second derivative of this guy, and this is the product rule, so we don't want to mess that up. So we have f double prime, and I'm going to plug in x's to start with just to kind of stay organized, right? F double prime of x is equal to, so we'll take we'll start with g prime of x times, this is going to be x squared minus x minus 6 plus g of x times 2x minus 1. And so kind of got it all broke down there. It's pretty nice. The thing, again, that I want to point out is as soon as we substitute in x is 3, this whole thing becomes 0. And so it doesn't matter what g prime of x is. This, we've already determined right above it that that's going to become 0 when we plug in 3. And so that's going to make life a little better for us. So f double prime of 3 is equal to g prime of 3. And instead of writing all this out, I'm just going to write times 0 plus g of 3 times 2 times 3 minus 1. So f double prime of 3. So g of 3 is negative 2. So this is all 0, so I'm not going to write this. We have negative 2 times, so 2 times 3 is 6. 6 minus 1 is 5. This is equal to negative 10. So we have a negative value. That means if we're negative, we're concave down on that interval. And if we're concave down and have a horizontal tangent line at that point, that means we have a relative max. So by the second derivative, test, f of x has a relative max at x equals 3. We're going to save example 5. We'll do that one in class next time when we get started. And so now you guys can start working on the homework.